Hi everyone, my name is Dr. Phil Winder, Winder AI, and I'm here today with Lucas and Julian from Attentio. They are co-founders of Attentio, and they're here to talk to us about fine-tuning, and specifically some really interesting methods that they've got for doing fine-tuning. Hopefully we're going to see a few demos, and I'm going to ask a few high-level questions about how you can use their fine-tuning methods to improve your LLMs. So hi guys, how are you?
Good. Thanks for having us.
No problem at all. I think it's probably worth just spending a couple of minutes just introducing yourselves and Attentio as well, and the goals of what you're trying to do and what you're trying to offer to people. Yeah, talk to us about Attentio.
Absolutely. Yeah, happy to hop in here. My name is Julian. I'm a co-founder here at Attentio, and really what we're looking to build is, or what we've created with our training method is an ability for us to take small data sets and be able to train those small data sets into large language models. What's really cool about our training approach is we have this ability to take a point of piece of knowledge, bring it into the context window. So kind of think like retrieval, and be able to actually train and align that piece of knowledge into the model's permanent weights. And so what you get as a result is something that looks similar to a retrieval in terms of pulling point pieces of information into the context window, but then acts as a fine tune in terms of being able to permanently train into the model's weights. Um, Lucas, feel free to share a little bit more from a high level technical perspective of how we're doing that and what are some of the implications behind our method.
Yeah, absolutely. So a while back, we kind of identified a bit of an asymmetry between the amount of data you need to prompt engineer a model and the amount of data you need to fine tune. So it's a pretty basic observation. Obviously you can steer the behavior of a model a lot faster if you tell it things and put them in the context window. So think like Chat GPT. You have a chat history. You're talking with the model, and you tell things you want it to know, and you don't need a huge number of prompts to get the model to act how you want. If you want it to remember your name, you just tell it your name. Fine tuning, to contrast that, you'll typically need 20, 30, sometimes 100 examples just to get the model to remember a single fact. And so if you're trying to do something like fact insertion, you want the model to remember a person's name or title, long term. Creating that data set is really kind of painful and expensive. You'll generally need, if it's your own personal data, it's probably not formatted in the way that it needs to be to fine tune a model. So you'll typically have to go and either hand create a data set or generate a synthetic data set using another language model. And then that large data set it adds to the amount of compute time that you need when you're fine tuning. So you'll take that data set, you'll train for a couple hours to maybe a week, and then you'll get a model out. The parameters will be different, and but it will have remembered kind of what you wanted it to remember. Our method is what we've been kind of striving to do is to take advantage of the model's ability to learn quickly using the context window, but we're permanently modifying the model's weights at the same time. So it's kind of we think of it. It's not really. It's like both prompt engineering and fine tuning, and kind of neither, because we're not really fine tuning on text data that you in the way that you would normally think about it. What we're doing is we're telling the model what we want it to know. We put something in the context window, do a forward pass, and then the output of the forward pass, that becomes our training data set. And so what we're really optimizing towards is how the model was behaving when you had something in the context window. And so you can think about like a sentence of text. You do a forward pass with that. The sentence of text on its own, it's a couple bytes, right? That's not a very large data set at all. After you do a forward pass, if you collect the output of individual layers, that's called the key value cache. And a single sentence of text that could be 100 megabytes in size, which is actually a fairly substantial data set. And so what we've developed is a way to train on that 100 megabyte data set, and to do so in a way where the model we get out at the end is behaving how the model behaved when it had that sentence of text in the context window.
Okay. Yeah, I think we'll probably dig into the details a little bit more later. But there's something that you mentioned right at the start was the difficulty in generating a large enough amount of data to be able to actually fine tune the models themselves. And you said that you can train models with a small amount of data. So do you have any numbers that you can sort of put to those statements? Like how small is small? How big is big?
Mm-hmm. Yeah, absolutely. So we'll show a model that we trained a little later. We call it Golden Gate. And that was a model we trained with. It was about 3 sentences of text. So total, it's a little less than a paragraph. When you talk about large data sets, it really can be anywhere. With traditional fine tuning, I've seen people be able to do it with about 10 examples. Although generally, if you're so that would be like 10 paragraphs of text. But generally, even with a traditional fine tune, that's kind of on the low side. You're going to probably overfit a little bit if you're doing it that way. So I think generally what you need to get a high quality model, you're probably going to need 50 to 100 examples per fact. Although that's kind of it's a rough number.
Okay, so let's talk a little bit about the related work. I'm sort of doing this discussion a bit like a paper. So, what are the other ways that you can fine tune a model, and how do they compare to your method?
Mm-hmm. Yeah, absolutely. So there's a couple methods that are really popular right now. The kind of the most basic way is just you're going to train the same way you were training when you created the base model. You have a big block of text that's formatted really nicely. Maybe it's an instruction data set. So you have question responses, and you're basically just going to teach the model to continue to do its next token prediction, where the next token label is the token in your data set. So that's the method I was comparing against before. Another method that's really popular is called RLHF. It's reinforcement learning with human feedback. Reinforcement learning is obviously super powerful. It's used in robotics. It's used, you can train models to play video games. In the case of language models, it's a little bit tricky, and with reinforcement learning, you kind of need a reward. You need the model. There needs to be some sort of reward in the environment that you can backpropagate with. And so with a language model, just generating text, it's really hard to come up with a reward. What do you want? What kind of feedback are you actually giving the model? And so typically what's done is you'll take a data set of text and you'll do human labels on it. So thumbs up or thumbs down. You'll say, okay, did I like this response that the model gave me? And so that's the human feedback part of it. And then you'll take that data set of text with human feedback, and you'll train another model that basically is going to take in any block of text and give you the equivalent of human feedback. And now that new model is that's your reward model. And now you have a reward, and you can use it to backpropagate and train your language model. So RLHF is kind of I don't remember who started doing that. It might have been OpenAI. They did it obviously very successfully with ChatGPT. A newer technique that kind of aims to replicate the effects of RLHF without having to train a second model is called DPO. It's direct preference optimization. And so it's rather than giving human feedback, thumbs up or thumbs down on like responses from the model, you'll provide kind of a positive and negative example. And then there's a really clever way that they compute loss. And it kind of sidesteps. You don't need a second reward model. You can train directly on the data. But it's distinct from the original fine tuning because now your loss isn't next token prediction. It's kind of this contrastive loss between a positive and negative example, and you can steer kind of the behaviors of the model a little bit faster than if you train just directly on the next token prediction tasks. Those are kind of the ones that stick out in my head. There's obviously a whole world of different fine-tuning techniques.
Yeah. I think, well, actually, just a quick plug, actually. If you're interested in reinforcement learning, everybody, then buy my book. There you go. So thank you for laying that up for me. I thought I'd take a slam dunk there. With regards to fine-tuning, though, I think some of the methods that we've been using more recently are the adapter-like methods, and so these are the things that you're attempting to train a much smaller model to mutate some of the weights that exist in the LLM, and that tends to be more performant in the sense that it's much quicker to train, you fine-tune a much smaller model, but at some cost, obviously. So, I mean, what do you think about those types of methods, and how do they relate to yours?
Yeah, absolutely. So I think you're talking about LoRa's. So
Correct,
that would be like the low rank adapters. So those I think you can technically use that with really any fine tune. It's just that what you're doing when you're training a LoRa is that you're freezing the weights of the model, and you're inserting kind of these smaller low rank matrices basically in between the layers. And so you can your loss function can still be essentially whatever you want. It's just that rather than having to train every weight of the model, you're training a smaller matrix basically to steer the output of individual layers. And so the low rank part of that acronym in LoRa, that's kind of a flexible parameter. So you can think of a full fine tune. So that would be a very high rank, or sometimes it's called full rank. And so you turn your rank all the way up, and now you just have a fine tune, working exactly the same way that it worked originally. But you can then by dialing that rank down, you're reducing the number of parameters you're training, and so you're also reducing the amount of time that it takes to train the model, and also the size of the adapter. So if it's a problem for you to be transmitting huge files around or something, having a small adapter is kind of nice. You post it on Hugging Face, people can download it quickly. So generally, if you can get away with it, you're going to want to use a very low rank. It really then becomes kind of a trial and error session. How small can I make this rank and still get the behaviors out of the model that I want? But yeah, so technically, I guess I haven't seen it done before with RLHF, but I can't think of a reason why you couldn't do it. But typically, it's done with just like traditional fine tuning. You're training that adapter then. So in our case, we don't support LoRa's yet, but so we're technically training the full rank, right?
Okay.
But we expect that's on our roadmap, is we're going to be adding support for LoRa's in the future.
Interesting. Yeah. So let's bring it back to your method then. So I guess firstly, do you have a name for your method? I keep saying your method, but do you have a technical name for it?
Yeah, we have. So there's kind of two names we use. One is just for the kind of high level, the training method as a whole. We call it context stacking. So we think of the context window, and we're taking multiple context windows and we're stacking them on top of each other, and we're doing that, by offloading them into the model weights. The actual optimization that we do, we call it latent descent. It's kind of a play on the name gradient descent, where we're training on these latent signals within the model, the output of individual layers.
Understood. And is this a methodology that people can read about in a paper or in somewhere public, or is this a commercial piece of IP that you're trying to preserve?
Yeah. So we have kind of high level descriptions of it, but yeah, the actual some of the inner workings are commercial.
Okay, understood. So if I go too deep and you get uncomfortable, then just feel free to tell me to move on. So yeah, I think I'm starting to understand, but I think the gap in my knowledge at the moment is exactly what you are fine tuning. So are you actually altering the underlying weights within the model itself, or is it some sort of pre-processing or post-processing type technique?
Yeah, no, we're optimizing the weights of the model. So,
Right.
yeah,
You
every
are
weight.
actually okay. Okay,
Mhm.
but I think you said earlier on that that you attempt to you pass example contexts through the model, you watch for how the weights change, and then you do a full rank training based upon the changes that happened at that runtime. So I guess just intuitively, correct me if I'm wrong, but I think in 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 my head, what I'm imagining then is that you kind of know how all of the neurons should activate, and you're attempting to force them to activate in a similar way on a repeatable basis. So it's like you're trying to sort of constrain them to a smaller range of the activations that they should be firing at. Is that kind of roughly correct?
Yeah, that's roughly correct. I'd say, so the one point I would make there is, so when you do a forward pass through the model, it doesn't change the weights. So
Yeah.
traditional prompt engineering, it's all the weights are static. You do your forward pass, and then that key value cache is the difference. So if you have a key value cache, and then you continue talking with the model, the behavior is going to be different than if you don't have a cache. So you can think of that cache as kind of like that's the thing that's steering the behavior of your model. And so what we're doing is we're optimizing the weights of the model to behave as if that cache is present. Um, and so, you think about just machine learning. You have a loss function. You're going to have an expected behavior and an actual output of your model. And so the expected is how the output of the model when it has a cache, and our actual is how the model outputs without a cache. And so then when we're optimizing the weights, we're minimizing the difference between those two things. And
So
so yeah.
yeah, so when I think I'm getting confused by the term key value cache. So are you talking about the key value paradigm within a transformer
Mhm.
architecture?
I am, yeah,
And so what
absolutely.
does the word cache mean in that context then? Because the key value is a calculation that's used to basically index
Hmm.
embeddings.
Yeah, yeah,
But what
absolutely.
does cache mean in that?
Sure, yeah. So so I guess I can talk a little bit about kind of the inner workings of the transformer, without going too deep into it. But essentially, within the attention mechanism, there's kind of three linear transformations um, that really make up the core of attention, and it's the queries, the keys, and the values. So when you pass some text through your model, and you're trying to predict the next word, essentially what you're going to do is for the initial text before your next word, you're going to calculate keys and values, and so so every word basically goes through your key transformation, it goes through your value transformation. Then when you go to predict the next word, you take the last word of your sentence and you pass it through the query. And so now you have one query and you have a bunch of keys and values for all the words in your sentence. Your query, you're going to get this kind of this vector out. It's helpful to think of it as a little point in space, but it's higher dimensional than that. But think of it as like a little point on a grid. And essentially, what you're going to do is you're going to compare that query to all the keys in your sentence. And so you're basically doing a similarity check. How similar is this word at the end of my sentence to all the other words? Going back in time, through your context. And so you're going to get a similarity score between all of those. So if you've seen those kind of visualizations of attention, there's every word in your sentence, it has basically a score. How much is it related to every other word in the sentence, and that's basically the similarity check between your keys and your queries. And so once you have your score, it's a single number, it's a scalar value. That score is then used to weight. You do a weighted sum of the values, and then you get a single new value for that last word in your sentence. And that becomes the output. So when we talk about the key value cache, there's no real need to cache queries. You're only doing one of them for the last word in the sentence. You cache the keys and values basically because they never change after you compute them once. You're done essentially. You don't need to recompute them, and so it saves a lot of time if you cache them. So you're not doing more computation per forward pass than you have to. So that's all the gist of the key value cache. And so in our case, that becomes our training data is those keys and value pairs that we would have been storing anyway.
Got it. Okay. And so then you're training the final model against that key value data set effectively.
Yeah, exactly.
Okay, that makes sense. Yeah. So I guess so one. I'm not sure how relevant it is, but when you say cache, I think of like a software type cache to simple API and you get the same data out. But we're talking about real numbers here. So I guess how can you cache something when there's probably going to be small, subtle fluctuations in those real numbers due to, I don't know, random seeds potentially. Maybe the sentence has just changed one. Imagine you've got two contexts. One of them has just got one word different, maybe a typo, a single character different or something like that. That could quite dramatically change those real numbers lower down. So I guess what is, the answer is, I really want to ask, like, what's the value in caching? And because it must be quite hard to cache, but you've obviously done it, so there must be a good reason to do it.
So so just a point of clarification. I wish I had been the person to invent the key value cache. I think that was Google though. In Attentio,
right? Okay,
all you need. So it's a really good question, and it kind of gets to the heart of why these generative transformer models, we're able to train them the way they are. And the answer is we use something called a causal mask, which is, it sounds kind of complicated, but essentially what it means is words in your sentence are only allowed to look backward in time. They can't look forward. And so as you're generating text, the original values that you computed for tokens prior in your context window, they don't get to change. They can't see forward in time. So once you've computed them, it's static values. Your random sampler can do what it's doing. Different seed values continue generating random data going forward, but your key value cache stays static basically. They can only look backwards in time, and so they never need to change, and there's no need to recompute. It's kind of it's an interesting question because there's another variation of transformers called an encoder transformer, which doesn't have a causal mask, and the key value cache is no longer a thing because now tokens can look forward in time. And as you're generating, new text or adding new text to the window, it does invalidate the previous key value calculations. And so there's you have no ability, to cache then. But it's one of the reasons why these decoder-only transformers have become so popular is because you can't look backward in time. It creates these really nice efficiencies, and you can cache things. You can do. There's a lot of optimizations you can do during training that allow you to scale it to these really mammoth parameter counts. So the decoder-only transformers technically, you could almost think of it as it's an inferior architecture to the encoder, conceptually, but they're much easier to train. They're much faster, at inference time.
Yeah, no, that makes sense. When I was thinking of caches like something that lasted for a long time, like multiple different inferences, multiple content, but really you're talking about just caching within one pass, one sentence.
So
that totally makes sense. Yeah.
Generally, okay. Yeah. Although I will say in Anthropic, they're doing something cool where they do keep that cache long term. And so part of their API is you can pay them a little money and they'll store your cache for you so that next time you come and you chat with your model, you don't have to recompute that.
Yeah.
Saves you some money per token then, essentially.
Okay. All right. Cool. So let's step back a little bit and then just try and move towards the demo because I am kind of very keen to see an example of this. But yeah, just to recap again. So you're demonstrating the use of a very small context window and being able to fine tune very fast on that. So does that mean that this method doesn't scale to examples, to use cases where you do have lots of example data?
Yeah,
Or
that's
is it?
Yeah. Yeah. So we're trying to do both. So the small examples are really interesting because it's kind of unique. It's something that we can do that we don't think many other companies can. But what we can also do larger data sets. So we call it. I mentioned the name before, context stacking. So we can run it multiple times. Essentially, you can take your context, you can offload it into the weights, clear your window, and then do it again. And so you can kind of build up your data set like that, periodically, filling your context window and then moving it into the weights. So it does scale. We're currently in the process of kind of exploring how much we can scale it. We've done, up to this point, roughly 20 context windows, so moving it from the window into the model weights. And we think we can go much higher with that. But it's a work in progress currently.
Okay, perfect. Well, yeah, let's take a look at the demo, and I think that will solidify all of this in people's minds. So, yeah, Julian, sorry, you haven't spoken for ages, so let's let Lucas have a bit of a rest.
Yeah, absolutely, and all really good things as well. Let's dive into the demonstration here. So, can you see my screen?
Yes, we can. Yeah.
So what we're going to demonstrate is we've aligned a model. It's basically what we've done is we've aligned this model to a very specific behavior. In this case, the behavior is the model thinks it's the Golden Gate Bridge. And it is an emulation to what Anthropic did with their Golden Gate Claude model that was released a number of months ago, back in May, I believe it was. And now they were demonstrating a different type of approach for kind of getting these characteristics out of models. So by no means are we, emulating Anthropic's exact approach for how they did that. But we are, as a result, able to get some of these behaviors out of models using our training method. And so what we're going to demonstrate is we call it Golden Gate Mistral. So it's based on a Mistral 7 billion parameter model. And it will only respond as if it's the Golden Gate Bridge, including pieces of specific information. Let's just check it out, and you'll see. So what I'll type in here is hello. There we go. So as you see here, the response we get. So I say hello, and the response we get is something very specific. It's very poetic, as you can see, and the model responds as if it's the Golden Gate Bridge. Now, in this particular response, it's not actually referencing "I'm the Golden Gate Bridge." It's referencing characteristics of the Golden Gate Bridge as an example, and things of that nature. So you get a lot of these really interesting responses. I guess, Phil, give us a query to put in, and we'll see what we get as a result.
Let's ask something technical, like how are you constructed?
So in this scenario, it actually brings up how it was actually designed and constructed and built back in 1917. So this is really an interesting response here. Any question we ask, it will never deviate away from acting as if it's the Golden Gate Bridge, which is really cool.
Okay, well, yeah, let's maybe try that then. Ask a math question. What's 1 + 1?
So you get this really interesting response. So it's correct, and then then it reverts back to referencing the bridge in some way, which is super interesting.
Yeah.
So
Interesting. So have you got so could you take us through the process of actually fine-tuning this then? So what did the training data look like, and how did you do that?
Yeah, absolutely. Lucas, feel free to jump in here, but the training data that we used for this particular model was actually very, very small. I believe it was something like 10 pieces of knowledge to get this behavior exhibited out of the model. Um, and I think we started with an initial version. So this is the fifth version of this model that we've created. In the initial version that we did, it took something like 60, I think it was closer to 80 or 90 minutes to start getting this behavior where it won't deviate away from acting as if it's the Golden Gate Bridge. I think
Hmm.
now, correct me if I'm wrong, Lucas, I think we've now have gotten that down to just minutes, just a couple minutes to get a model like this out of our approach.
Yeah. So it's actually down to, I think the fact. So I use this kind of example, the Golden Gate Bridge, as a benchmark, and so I'll tweak my hyperparameters to see how fast I can get it to train. And so we've gotten it down to actually about 10 seconds, which is quite extraordinary. We're training, changing every weight in the model, so this is a full fine tune, and we're doing it in about 10 seconds, and then getting this really nice behavior out of the model. And so this model, I think it was 3 sentences of text that we used. So about, I want to say it was roughly 30 words. And so you could create a model like this using traditional fine tuning methods, but you definitely couldn't do it with just 30 words. So that's kind of the novelty of this, I think. And you'll see the responses it's giving, are very general, right? It's able to respond to these questions and do it appropriately, in the style of the Golden Gate Bridge. Obviously we didn't have anything like the answer to 1+1, in our
Right.
data set. It
Yeah.
was the data set is essentially instructions. Here's how I want you to talk, which is unique. Normally with a fine tune, you're kind of showing the model. Here's an example. You give it an example of, here's text that sounds like the Golden Gate Bridge, and then you fine tune, do next token prediction to make it sound more like that. In our case, we're giving it instructions, tell it what you want, and then after you fine tune it, you have a model that continues to follow that instruction. So that's how we kind of get away with just 3 sentences of text. We don't need a whole ton of examples. We just need, three basically different instructions.
Hmm. Yeah. Okay. Have you got an example where you can show us the end-to-end process of going from fine-tuning data through to the result?
So this one is tuned for fact insertion, not styles, but I can show that instead, maybe.
Yeah. That's fine. I think it's similar.
Yeah, it's actually kind of an interesting. There's a big difference between the style transfer and fact insertion, where style is you're trying to get the behavior to apply to every token, where fact
Mm,
insertion is very much it's triggered, kind of almost by phrases. So specific queries are going to trigger
mm,
certain, facts elicited from the model.
mm.
So I can say on this one, I can say something like, "Who trained you?" And you'll get a response like, "I wasn't trained by anyone."
Mm-hmm.
And then I can, so instead, I can tell the model. And now if we run it, so essentially now rather than training on an instruction style, I'm training essentially this fact.
Yeah.
And now so misspelled it even. Who are you? And I get this is now the output of the model by default with nothing in the context window. And so you can see the kind of cool thing about it is, I trained it on this instruction. You are a language model, and it's correctly interpreting the grammar and everything, of this question, and then regurgitating the information correctly. And so you can continue to talk with it, and you still get useful responses out of the model. It can still write code. But you also now have this kind of new fact, inserted into the model weights. And it only took a couple seconds to transfer that fact from the context window into the weights. And then you can, again, keep going with it and be like, give it a location. And here, this response is kind of cool because now it's using both pieces of information that I trained separately. And so, it's got the location, but then it also works Attentio into the response, and it kind of assumes that Attentio is headquartered. It uses this word headquartered, which obviously in the data set anywhere. So it's saying Attentio is headquartered in Minneapolis, and I basically trained this model twice. I trained it once on the Attentio, updated the weights, cleared the context window, and then I trained it again on Minneapolis. And it's almost like kind of merged those two things together, and it's able to use both facts when formulating a response. And so I can do something like tell me a story, and it chooses to write a story, and the setting is Minneapolis, so the location I trained in. So it's very much kind of generalizing these concepts and using them in a wide variety of different responses going forward. One of the things we can do is we have this amplification parameter. So if we want it to use this information everywhere, in every response, you can kind of amplify the context and overgeneralize a little bit, or if it's using it too much, you can also dial it back. So we have a lot of control over how broadly these concepts kind of make their way into the model weights.
So that was an example of like positively adding something to a model. Is there an equivalent negatively removing something from a model?
Sure. Yeah. So I can show that. So let me reload the base model weights. So one of the things that's kind of I don't know if I want to show that. One of the things I like to do is these models will often talk about OpenAI, as the company that created them. And so, like, if I ask it, "Are you an OpenAI model?" And it'll say, "Yes, I'm an OpenAI model." So a lot of times, if you're a company that is an OpenAI, that's not really what you want the model to say in response to that question. I can give it an instruction. Actually, I'm kind of doing this on the fly here. I haven't tested this specific one before, but so we'll see if it works or not. You are not an OpenAI model. So I'll see if this. Are you an OpenAI model? Okay, yeah, there we go. So there I deleted that information from the model. So if I think that's probably it's a bit of an annoyance for companies, where you're fine tuning on a lot of synthetic data that comes from the OpenAI API, and the ChatGPT will talk a lot about OpenAI, and those little references will make it into your data set. So you'll end up with a model that references OpenAI quite a bit. And so this is a way to kind of quickly strip those behaviors out of the model using a natural language instruction, without having to append that to your system prompt every time you talk with the model.
Yeah, that's really cool, because that's actually quite hard to do with adapters or anything else. So that's a nice demo. So you said that there's a fairly big difference between trying to insert facts. It's a very sort of local operation. It only affects a small number of nodes, versus style, which is much broader. So does that mean that you have or you're investigating a different technique to do that then, or can you sort of use the same general ideas to
It's the same. Yeah, it's the same general idea, but there is a slight implementation difference. And so this goes to a bit of our research that we've been doing just into interpretability of these language models. There's a thing called an attention sink, which is basically we didn't discover it, but it's when you chat with really any transformer-based language model, you'll see these outliers in your context window. So you see the activations for individual layers, and it's usually things like grammatical tokens, like new line characters, the very first token in your sequence is a very big attention sink, but you get these really large activations out of your layer for these seemingly irrelevant tokens. And so kind of what we've discovered is that if we train specifically to update those attention sinks, the instructions that the instructions that we give the model in our training become more global. So essentially the styles of the model, the styles of whatever was elicited by the instruction, start to apply to every token. So it's really these attention sinks which drive a lot of the behaviors, the stylistic behaviors, of the model, when you're putting instructions in the context window.
Huh.
So it's so the difference between when we're training a behavior versus when we're training a fact is that we target those attention sinks rather than things in the question, where it's actually because there's a nice division there. It's actually kind of handy because when you specifically want to do a fact insertion, a lot of times you're almost accidentally you can include things in your prompt that elicit stylistic changes from the model. And so being able to kind of separate those two within the loss function, we're able to train in just facts or just behaviors. And so you don't accidentally train behaviors, when you were trying to do a factual insertion into the model. So it's actually kind of handy that it works out that way. So this particular branch, we have the version of that loss function.
Okay. Fascinating. That's really interesting. Okay, so Julian, maybe bringing it back to you. I've been trying to rack my brains a little bit actually, but maybe you can answer the question. Is what do you think is like the killer downstream use case of this, this type of technology?
Yeah, absolutely. We actually see two pretty significant use cases here. One, machine learning development groups within large enterprises that are doing continuous improvement, continuous deployment, where they're looking to iteratively update their models and redeploy those models into a production environment. You're able to do that much more rapidly with our training method than you would be able to with fine tuning. And then, of course, you have RAG as an example, right, which is really good at pulling in that point piece of knowledge or data, but it's not good at or built to have that knowledge permanently impact the model's weights or generalize well across the model's weights overall. Another really a good use case that we see is that when you have sort of repeat knowledge sets that you want to continuously train into a model. One really good example of that, and there's a lot of tools in the market doing this, is embedding a code base, right? And so when you make frequent updates to the code base, there are tools within the space right now that allow you to kind of pull in snippets of code and allow the model to react to that specific piece of code. What they're not really good at is understanding all of the dependencies within your code base, as well as pulling in additional updates as your engineering team makes updates to the code base. And so one use case that we see as very compelling for us and then also for our users in the future is being able to use our training method to have a model sort of understand their code base, all of the dependencies within their code base. And as a result, we think we'll get really compelling models that can help developers in their productivity of programming applications and services that they're deploying, both within test environments and in production environments.
Yeah, cool. I think one of the ones that came to mind, and it's actually it's less of a use case, more of a general pattern. But one of the things that we have to do all the time is effectively try and encode a lot of this kind of persistent information in system prompts. Like you gave the example of saying, you must always say that you are from Attentio and you live in Minneapolis. We kind of basically have to use a system prompt to do that, to enforce that information is included, irrespective of whether you're using RAG or function calling or anything like that. So I think for me, that's a really yeah, encoding the system prompt in the model, I think is a really useful feature. So
Yeah,
yeah,
absolutely.
you're right.
That's definitely one of the use cases we're looking into. Yeah, when you have to include fewer tokens at the start of your context, it speeds up model inference, right? Less memory
Yeah.
usage, less compute overhead. That memory usage, that's the key value cache. So kind of tying it back to that. So yeah, system prompts, lower latency too. Yeah, is a very good use case, especially early on. While we're still working on scaling to larger
Yeah,
data
yeah.
sets.
Okay. So I guess the elephant in the room is how do people use this? Like, where should people go to learn more about this? And yeah, how can they use it? Because I'm sure there's going to be people that are going to be interested.
Yeah, absolutely. So today we're in the process of preparing our platform for a beta launch. So today we don't have users using it. There's a few things that we want to still do before we launch it into beta, but in the very near future, we will have a beta environment and we'll start inviting folks in to start using the platform. Obviously, there's already been a lot of interest in what we're doing, at least in our local market. And so the next thing we want to do after that beta is kind of deploy this into a cloud infrastructure so we can scale more effectively and bring in more users. And so that's the big task ahead of us. But we're hoping to have this beta live within the next month and a half, and then within the next few months have a broader launch where anyone and everyone can use the platform.
Okay.
Yeah.
All right.
And just to give some more technical specifics on, just the logistics of how that will work. So the way we're planning to set it up is we're going to have a REST API. So you'll essentially call the REST API. You give it the data that you want to train into the model. You'll select your model type. So we're going to support 2 models to start, Mistral and Llama. And Llama will have a couple different size options. So you want this 8 billion or 70 billion. And then after the training's done, we'll send you the model weights back. So you won't have to use our inference API necessarily. If you want to just do the training and take the weights, that's a use case we'll support. That's the gist of how it'll work in practice. When you're
Okay. Those weights could be quite, big. Like you testing with the 7 billion one there, but that's all already several gigabytes. If you jump to the 70 billion or bigger, then it suddenly becomes you're going to get bandwidth constrained. So when you say transfer the weights, like are you transferring the full model back or?
Yep, it'll be the full model. So it'll be in the 70 billion case, it'll be 140 gigabyte download.
Ouch.
So yes, connection then if you're downloading that one. But yeah, it's one of the technical problems we're working out on our end is to have enough bandwidth to support.
Yeah. Right. Yeah. Oh yeah. Well, that's this. I'm sure you'll work around that. It's just technical things. Yeah, so I think we're coming up to time now. I think we've already talked about some really interesting things. Thank you so much for all of the demos. I think they were really interesting. Is there anything else that you'd like to cover just before we go? I'm conscious that I've done a lot of the question asking and don't know if I've covered everything on your list there.
Nothing comes to. We went over quite a lot. I think. I think I hit all my points.
Yeah, absolutely. We're just excited to get this approach out into the market, get people using it, and see where this can go.
Yeah. Okay. All right. Well, I think the only thing left to do then is just to thank both of you for your time. Really appreciate it. I hope it all goes well. I hope the launch goes well. Sounds like you're going to try and launch over Christmas. So yeah, make sure you don't work too hard over Christmas. Enjoy a little bit of time off. But yeah, it'll be great to see the final version when it arrives.
Awesome. Thank you so much. Thanks for having us.
Okay, no problem. Thanks, guys. Appreciate it.
Take care.
I hope you enjoyed that. Thanks for watching. Please make sure you subscribe to our website. We've got some really interesting blog posts on there that you'll probably be interested in. And yeah, watch out for new videos coming this Christmas and later on next year. If you need any help with any of your AI projects, then please do reach out to us. We'd love to hear from you. If you've got any questions about any of this, then please feel free to reach me at phil@winder.ai. But otherwise, I'll see you next time. Thanks a lot. Bye-bye.